Hello everyone, and sorry for the delay. So I'm happy to start the new semester in our learning club. And today we lost Matthew Ricci. Matthew is a Superman postdoctoral fellow studying machine learning and dynamical systems, particularly network systems in biology, and in the lab of Morning Sun. Today he will talk with us on hypernetworks approach to controlling and exploring families of dynamical systems, titled Go with the Flow. So the stage is yours.
Okay, excellent. You hear me well? Yes. Okay. As my host said, my name is Matthew Ricci. I'm a postdoctoral fellow here in the lab of Moore-Nitzan, and I'm very pleased to be speaking with you today about a research program in our group concerning specifically machine learning techniques for understanding families of dynamical systems. And without further ado, let's go with the flow, as they say. So I'm particularly interested in dynamical systems and families of parameterized dynamical systems because I think they exhibit an interesting phenomenon which intrigues me in nature. And that's that they exhibit two things simultaneously. On the one hand, they can give rise to these small continuous changes. So, for example, here we have a depiction of what it's like to be a postdoc. We have a picture here of the Tacoma Narrows Bridge in 1940, which is undergoing these smooth but still troubling variations in a torsional wave because of a famous construction flaw. And so you can have a subject to certain parameters of a physical system, small changes which are not dire, but still maybe a little troubling in some cases. And they're troubling because perhaps they forebode the next type of change which these systems can exhibit, which is not a small continuous one, but a large categorical one. So this actually happened. If you've seen the videos of this, it's kind of amazing. And so, like many things in nature, we have the cohabitation of both small continuous changes and large discrete changes. And I think that this is interesting from a kind of pure science point of view, but also from a machine learning point of view. It makes it ripe for data scientific investigation because much like, for example, language and vision, we have the cohabitation of small continuous changes which we are forced to, for practical or kind of psychological reasons, to discretize into big chunks and big events that we call categories. And the great thing about physical systems and dynamical systems is this distinction between the small quantitative change and the large categorical change is in fact mathematically rigorized, which we'll discuss in a little bit. Let's hope that the talk goes better than this. So in the Nitzan group, we're particularly interested in a certain type of physical system, certain type of dynamical system, namely biological systems. So here I've depicted a certain type of dynamics in the form of interacting cells. So cells in tissue will send each other signals in time about what to do, how to grow, when to stop growing. So in normal circumstances, we'll have a network of cells interacting with one another and sending each other signals saying, okay, continue to grow into this structure and eventually stop. And you can have small, subtle variations in how this works, and that's akin to this continuous small change, but you can also have these categorical, or sometimes we call catastrophic shifts. And so you can have a catastrophic shift in the dynamics of cell-cell interactions into runaway excitation, which might result in something truly dire like runaway growth in the form of a tumor. And it's a natural question, empirical question, in the case of biology, to ask what are the underlying parameters between this type of system and this type of system that give rise to those categorical differences. Are they genetic? Are they environmental? Etc. And there's already quite a lot of work in machine learning concerning dynamical systems, but I would argue that it's all of what I would call the system level. And I'm going to make a distinction between the system level and another type of level. So by the system level, I mean that when a machine learning scholar tries to understand a dynamical system in the world, he or she will do the following thing. First, we'll take a look at a system by examining it as it evolves in time over many different initial conditions. So you push it around, you observe what it does in time, and you want to ask the question, what are the underlying parameters? In the case of this bridge, what's the torsional velocity of the wave? What's the tensile strength of the cords that are holding up? What's the wind velocity or something like that? You want to reconstruct the parameters. And the traditional way of doing this these days in machine learning is you take some high-dimensional signal from observing a particular state, like all the velocity and momenta of different points of the bridge. You say, let's take this high-dimensional signal, map it to some reduced space where we can pull apart the factors of variation that give rise to the particular way that this thing is moving around in time. And we want to answer the question, typically, what are the parameters of the system given the representation we've learned of the state? So we're fundamentally working at this kind of state system level. But when we're starting to talk about big shifts in parameters and catastrophes that can happen not just with one system, but transitioning from between systems, we have to work at another level. And this is one of the general themes that we're talking about in our group. And that's to move from the system level to the family level. And so now a family of dynamical systems is not just one thing changing in time, like a pendulum back and forth as its state moves, but rather a collection of, let's say, different pendula, or collection of different bridges subjected to different parameters. Maybe those parameters are, for example, wind velocity. So now we're not just looking at a system evolving in time, we're looking at a family of systems which are parameterized by certain variables. For example, in this case, wind velocity v. And this leads us to all sorts of different interesting questions, like, as v is varied, at what point do you go from a drivable, nice bridge to something that looks like this? So an example problem would be, can we predict when a catastrophe is going to happen as system parameters are varied? So what we're thinking about here is a transition from system level modeling, where we want to take a single system and understand it, to family level modeling, where we want to look at a perhaps even uncountable collection of dynamical systems, and we want to ask, what does this subfamily do? What does this subfamily do? What are the behaviors that it can exhibit? And in a sense, this is just, I'm just describing what physics is, right? Because in physics, you have a system, and it's got some parameters, like it's an icing model, or a collection of cells, or a flock of birds, or the economy, or whatever, and you make measurements in the form of how fast the birds are moving, how fast you're losing money in the economy, or something like that, and you want to understand, you want to learn some function that goes from the underlying parameters to the observables of the system, so you can make judgments about when to sell your money, when to avoid the birds, or et cetera, et cetera. But this is famously not forthcoming. Physics is hard. So instead, the kind of general gesture that we're going to be looking at today involves a detour through another type of node in this kind of scientific diagram. And the basic idea is that we're going to, instead of trying to analytically understand this map, we're going to play around with a collection of systems which are somehow inherited from this parameter space. They're not directly, necessarily, just the systems that these parameters determine, but they're somehow useful to us from an engineering point of view. And what we're going to do is, instead of trying to just learn this map analytically, we're going to make measurements to this system and ensure that it's differentiable in a sense, for example, by playing around with neural ordinary differential equations, which I'll describe in a little bit. And then we're going to do our favorite thing, which is just calculate gradients so that we can understand how parameters and observables relate to one another. And inasmuch as these things end up looking like neural networks, which they will, the map from the parameter space to this we can think of as being a little bit like what people call a hypernetwork. And that means a neural network whose output is itself a function or a neural network. This is not the sense in which hypernetwork is used in the pure machine learning literature, where it's really just a way of kind of regularizing the learning process of another neural network. But nevertheless, in as much as it is a kind of meta network of these things, that's the term what we're going to use. And this is the big picture. And what we're going to do is we're going to outline a couple of basic concepts involving dynamical systems, families of dynamical systems and how they interact with data. And then we're going to return to this big picture and say, how can we apply it in two major settings? And those major settings are fall into two categories: control and prediction. Control means we don't necessarily just want to learn this map from parameters to observables for its own sake. We want to be able to take a dynamical system and force it into a target state. This is like autopilot or something like that, where the plane has to adjust in some automated way to accommodate for changes in wind velocity and things like this. So control. And then maybe we just want to learn something about the parameter space. Where the catastrophes happen, what are the different types of behaviors that this system can undergo, this family of systems can undergo. And those are the basic two things that we'll discuss after we work with some basic terminology to start. But before I continue, I'll ask, are there any questions? I might have seen one right here.
Yeah. I don't really know much about dynamics as a computer scientist. But, so in the example of the bridge, the first, like the system example, then you would say, like, I would want to model it as like a differential equation.
Mm-hmm.
That would be and then the system, the family, like how would you describe it in that term?
Well, in a sense, it's the difference between a differential equation and a parameterized family of differential equations. And what we might do here, in this case, if we were just asking what are the parameters underlying the system, we could do things like measure a trajectory of the system as it evolves in time. So you get a time series, basically. And then what you would like to do is maybe you have some model of the way the system works, but you don't know what the parameters are, you just fit the parameters or something like that. And at the end of the day, what you're given is a set of parameters that define this system's behavior, and then you can stop. And that's an important problem, right? It's a reconstruction. But what you're not doing is you're not saying how this system relates to another system. And if you were to do that, instead of learning, for example, a representation of a trajectory, what you would like to do is you would like to take a full differential equation, in a sense, right, of all the different initial conditions, and you want to take that mathematical object and you want to map that to a point. So the difference is between learning a representation of a state or a trajectory, single trajectory, and learning a representation of a family of trajectories. And I hope that this will become a little more clear when we start to look at pictures of families of trajectories that encapsulate a full system's behavior, not just under one trajectory. I think this will become slightly clearer as I continue. Are there any other questions? Excellent. Okay. I've been perfectly clear, I'm sure. So let's do a crash course in dynamical systems. So what's a dynamical system? What's a real dynamical system? We're not going to be talking about discrete maps or things like this. So dynamical system is what a physicist calls a family of differential equations, a set of differential equations. And we would use it to describe usually how some physical system changes in time. It's not a technical definition, but it's the colloquial one. And so we might have an equation that describes the first derivative of the system, which is indicated by this dot, and one describing the second derivative of the system. In general, we're going to be looking at first derivatives here. And these equations describe how the system changes in time. We refer to x as the state of the system, and we say it lives usually in RD, or maybe it's on some other manifold like the sphere or something like that. We refer to the f as the equation of motion. It's a little bit of a classical term, and that describes how the system changes in time. Lambda is a parameter, or more generally really a vector or set of parameters. And if we want to know how this thing behaves, if you remember your high school physics class, we need to know an initial condition. Pick an initial condition, and you solve the system, and it shows you how the system evolves through that point. That's a real valued dynamical system, usually the state space of RD or something like that. So we can play around with some other notions too. In general, for example, if you have a given differential equation or dynamical system with the equation of motion f, we can define another map called big FT, which goes from the state space to itself. And what that's going to do is it's going to take a state at time little t, and it's going to map it into the future. And it's going to say, where does this thing go? Where does it flow? And in fact, That's what this map is called. It's called the flow associated to little f. And the way it's computed is by taking an initial condition of the state at time t and just integrating the equation to motion. If you've played around with numerics or numerical dynamical systems, this is just something like running Euler's method to get a trajectory or something like that. And this is a generalization of the notion of fluid movement. So you have water or flow or something that's pushing a state from one state to the next. And the nice thing about this map is it's mathematically a homeomorphism, which means it's a continuous function which is invertible with a continuous inverse. And that's nice because it has these nice properties that on the state space it will act as a kind of continuous warping, like you're moving around a rubber sheet. You're not tearing holes, you're not doing anything too strange. And so this flow is a way of pushing around states, and it's a concept that we're going to make use of a little bit later. So math is great, right? But in general, if you can draw a picture and understand something, you should. And I like the kind of Strogatz way of thinking about this, which is instead of doing math, draw a picture. So for example, here is an equation which describes a dynamical system which was examined by our colleague Miri Adler in a recent paper. And it describes, for example, the interaction of two genes that mutually reinforce and inhibit one another. And it's got these equations involving kind of Hill functions or something like this. You don't want to play around with it. So instead what you can just do is you can draw a picture. And what the picture shows you is how the variables x and y, in this case maybe the activation levels of two chemicals or something like that, change in time, given a particular initial condition. So for example, I would start up here, and then I would run my system, and then I would follow these lines, which are called integral curves. And the nice thing is you can just look at this, and you can tell something about the way the system behaves, and it gives you a portrait of the way the system works, which is why it's called a phase portrait. And you can tell that because of this kind of swirly-whirly business in the middle, it's approaching something like an oscillator. And indeed, under some parameters, it is an oscillator, so that the system will start here and kind of play around like this for a little while. And this is called a phase portrait, which is another way of thinking about these systems, and is often more useful than actually doing math. So, what do machine learning people think of this? Well, it's an interesting opportunity because dynamical systems are everywhere. Physics is, in a sense, a dynamical system. And so we have these great, new, interesting models for exploring these interesting objects. So what can machine learning do for dynamical systems? Well, here are three recent examples. In a paper in PNAS from Steve Brunton's group, they proposed the so-called Cindy model, which can take high-dimensional dynamics, trajectories through a high-dimensional space, and find a reduced coordinate system. So maybe you have really a dynamics which is one-dimensional, moving back and forth on a line, but you have all sorts of high-dimensional noise or measurements like that. And what the system will do is it will take the system as it evolves in time, xt, and it basically play around with an autoencoder and map it to a lower dimensional space so that you can reconstruct a trajectory and probably some of its derivatives too. More or less the same thing was done a year earlier, specifically in the case of spiking neural networks, or spikes in biological neurons, in the so-called LFADS model. More or less the same thing, an autoencoder for learning the dynamics. And closer to our heart in our group was a recent paper from, I think, Cell Systems, in which a recurrent neural network was used to estimate the dynamics of a gene regulatory circuit exhibiting a particular function. And the way this worked was they would graph the trajectory of a target function, and they would just ensure that their little neural machine here, when it output the derivatives of their dynamical system, ended up looking like this. And again, it's for single systems. So the knowledge that's stored in these learned parameters in all these systems is the knowledge to reconstruct a particular object, this circuit, that cell-cell network, this dynamical system. In no sense are we looking at an embedding which will tell us how one transitions to another, how a family behaves. Yes?
So what exactly is the value of this for a scientist? I mean, Why is this paper in 10AS or whatever it is? What is it used for?
Well, you could use it, for example, for a type of dynamical denoising. Maybe you don't know what the true coordinate system of some noisy time series measurements are, right? You're just given some noisy measurements, and the way this works is a type of symbolic fitting. So you have a family of basis functions that can comprise your equation of motion. And so maybe you don't know if the system involves interacting sinusoidal couplings or polynomial terms. And after you fit this to some data, you'll get a reduced equation, which you can just put on the table and say, yes, the underlying dynamics of this thing that I measured in the world are two interacting variables with a sinusoid and another one with an x squared. And maybe if you're an engineer, an x squared is a terrible thing, and so you would say, I'm glad I knew that. And then maybe in this case, you would want to understand, for a particular biological function, which genes need to interact with one another. And this little object here will be able to spit out a little network and say, I think that gene A is interacting with gene B, but not gene C. And then maybe that informs a prediction about clinical work or something like that. Yes?
Can you decode the differential equation from this, or is this just kind of black box?
This one you can, definitely. And it differs from application to application. So this one is explicit. You're fitting particular terms, a sine term, x cubed term, or something like that. And then you can just put it on the table and look. This one, you can't. And this one, I don't remember. But it differs from case to case. And it's the same thing with machine learning. Sometimes you want it to be explicit, and sometimes you don't care. Any other questions? Okay. So lots of great ways of doing this for understanding particular systems. And I would be remiss before a machine learning audience if I weren't to talk about the sister program, which is what can dynamical systems do for machine learning people. So famously, Chen et al., I think, in Norup's paper from a couple of years ago now, generalized the kind of discrete layers of a residual network to a continuous time network, which they called a neural ordinary differential equation, whereby the action of discrete layers in a neural hierarchy are replaced by the action of a continuous time neural block, which is acting on, for example, an image. And this has certain advantages because you don't have to just evaluate in discrete steps. You can evaluate whenever you want in time, et cetera, et cetera. It's automatically invertible, what have you. Another paper which came out recently about the interaction of, or the benefit of dynamical systems for particular deep learning was from Joan Bruna's group, who I believe was here recently, about...
By Zoom.
By Zoom, okay, yes. He was here. Using dynamical systems to understand the learning process in a deep network. Here I'm showing the flow of, I believe, some quantity having to do with the output of a particular neuron, or measurement of a particular neuron as a function of the gradient in its orthogonal complement or something like that. I don't exactly remember, but keep in mind that when you train a neural network, you're doing something like dynamics. You have parameters changing in time. It's evolving. If you've ever written out gradient descent, that's a gradient flow, my friends. Okay, so this is about learning states and modeling states, but what happens when we start to play around with parameters? We get into this family domain. Well, we can get both quantitative and qualitative effects. So imagine we have an oscillator. It's spinning around happily like this, and it has some parameter. This is a phase portrait, so you can see one trajectory as, for example, the real and imaginary parts change in time. So if you wiggle around lambda, you can, for example, play around with how fast this system approaches its fixed point at the origin. So that's nice. But you can get these catastrophes, or these categorical changes, when the parameter lambda exceeds some threshold. And all of a sudden you get something that's genuinely new in the form of not continuous change in how fast this thing moves, but rather the emergence of a topologically new structure in the form of a limit cycle, indicated by this blue circle. So whereas here, these points will go towards the origin forever, no matter where they started. Here, if they start out here, they're going to zoom into this guy, and be stuck there forever, and they start in here, they come like this. That's a categorical shift, which is just definitively not found in this type of system. And we refer to this categorical shift as a bifurcation. One thing splits into another thing. And bifurcations are interesting and great because they mark boundaries in the parameter space, big lambda, between dynamical equivalence classes. And I mean this in the technical mathematical sense. So for example, here is a two-parameter model of an epidemiological network from Gross and Blasius from almost 15 years ago now. And what you can do is, with some analytical methods, you can partition the parameter space into zones which show what the general behavior of the dynamics are. Is this epidemiological network bistable or healthy or endemic or something like that? I'm pretending like I really know what those mean, but I don't. Nevertheless, you can get these nice equivalence classes. And this is a technical notion, the equivalence class. In particular, if you have two flows on RD, same state space, we say that they're equivalent if there exists a homeomorphism at H. This is this kind of continuous warping, whereby this relation holds. And this looks a little bit complicated. It will remind you of some things in abstract algebra if you've taken that before, but essentially it says that the behavior of F is equivalent to the behavior of G modulo a little bit of foolishness with H. So you can kind of push around this flow and you can always recover H. And in this case we call F and G topologically conjugate. We say that they're equivalent, and crucially, their dynamics are identical. They're topologically identical. Same number of fixed points, same number of limit cycles, they behave the same way. And so if you prefer one to the other, you can work with that one if they're topologically conjugate. It's a very nice notion. Okay, so those are the basic concepts. Let's do something with it at this family level for machine learning. So you'll remember our big picture where we're going to we want to learn this map, and what we need to do is figure out a way to use backprop, basically. And the two main applications are going to be control. We want a system to do a particular thing, and prediction, where we want to just learn the structure for its own sake, and we don't necessarily need to force anything to do, assume a particular behavior. So these two applications first will involve some published work involving control, and then after that we're going to talk about some ongoing work, which is the more biological stuff, which is going on in the Nitzen lab with two audience members, as a matter of fact. Are there any other questions before I continue? Okay. Yes?
The capital F and capital G in the full stack, they represented one differential equation.
This is one flow, so it's the map that goes from state to state that says, really there should be a sub t here or something like that. And so this really should say, it says for all t. So this is saying if you can take an orbit, a trajectory to the state space, you can always warp it into the other one in this kind of continuous invertible way, then the systems are the same. Because you can, in your mind, you can analogize these two mathematical objects to the set of orbits or set of trajectories. And this is just saying that you can continuously deform one into the other.
So flow from a mathematical perspective is just path, or
is just
path. In analysis.
Yeah, sure. Okay, so let's talk about some applications, unless there are other questions. Okay, there'll be questions afterwards if we have enough time. Okay, so we want to control things. What's one thing we want to do? What's a system whose state we want to influence? Well, one thing we want to do is we want to classify stuff, right? We want to classify data, and famously data is entangled. I know there are people here who work on entanglement, especially in natural image or natural data classes. And here's the simplest entangled data class I could think of, where you have samples from two classes. You have a sample of this green class in the plane, which lives in this disk. You have a sample of this orange class, which lives in this annulus. And what you'd like to do is you want to learn a representation that makes these things linearly separable. And traditionally what you would do is you would lift this center disk out of the plane by mapping this to R3, and then you draw a hyperplane, right? Okay, and now imagine that you're playing around with flows and dynamics, as people in the continuous time neural network business do. Well, then you're out of luck if you're working with one of these systems which can only carry out this flow, as you mentioned. Why? Because a flow is a homeomorphism. And homeomorphisms preserve the topological structure of data. And so if you try to classify this data by learning a neural ordinary differential equation that tries to warp this data space in some continuous way to separate the green from the orange class, you're out of luck, right? Because the linkage here is a topological invariant, and so the homeomorphism is simply going to push around these initial orange and green states to these black states and kind of mix them all together in a way which won't make them linearly separable, at least in the kind of continuous limit. If you have finite data, then you're okay. And so what we can do is we can make use of this notion of catastrophe and this notion of family by invoking bifurcations to simply tear this apart. We will tear these data sets apart by not learning a single flow that will kind of warp the whole system, but rather a family of flows. And this is work carried out with my colleague at Brown University, Mathieu Charles-Vidal, in a paper from ICR last year. And the idea is that we want to learn one dynamics per point in the plane. So every point here is going to have its own flow, so that if you live in the green part, your flow is going to say, stay where you are. And if you live in the orange part, your flow is going to say, go over here. And in a sense, that will make the underlying data space a little bit like the parameter space of a family of dynamical systems, which is going to bifurcate in a non-technical sense along the desired decision boundary. So this is most clear from a very simple example when you try to learn a simple reflection function. F of x equals negative x. Do you have a question?
Yes, please.
Yeah.
Could you go one time?
Of course.
Each point is a different dynamical system.
Each point is associated to a dynamical system which is learned.
To single sample of a dynamical system.
Each point here has associated to it a particular equation which is learned, which is a function of that point. And that equation will push it around, basically. It will flow in a dedicated way, in a data-dedicated way for each point.
So the lines are they a single, like a time course? Or
yes, the lines here show how, in the case of the neural ODE, the one point transition to its final destination at the black X. Here is the same thing. The only difference is that now you have one dynamics per point. Here you have one dynamics for the whole thing.
Still a bit confused.
Uh-huh.
So each point is a different system?
No.
Yes.
No?
Yes, in this case, each point is associated to a different system.
There's one system out, and every point is a different input. Right?
Yeah, exactly.
Oh, okay, different initial conditions for the same system.
Exactly.
Okay.
Whereas this, you have one system per initial condition. It's almost overkill, right? But what you're going to do is you're going to learn a dedicated system for every initial condition. Does that make it?
Like from single samples?
Yes. Every sample is going to be mapped to a differential equation, which is going to push it in its own dedicated manner.
Isn't it too much freedom? Like,
In a sense, maybe it is too much freedom, but it works. I don't know. Is there a question there? Okay. Okay. You can see the advantage topologically most clearly if you're just trying to do something like learn the reflection function f of x equals negative x. And so here are the action on the unit interval, or the interval from -1 to 1, of a neural ODE and our system, which we call, because you need a fancy name for everything, encode for neurally controlled ordinary differential equations. And you can see that as the system evolves in time, if you're only working with a homeomorphism, then you're out of luck because trajectories can't cross. That would mean that the homeomorphism is not defined. But if you've got one map per point, then you can cross to your heart's content. And in two types of systems, you can either have feedback or not, and we would call that open versus closed loop, which is a term I'll define in one moment. Yes?
So what's the goal here? Is this just another way of doing classification, or?
It ends up being a kind of general purpose mechanism. We use it for both discriminative and generative tasks, and including one that's a little bit of both. But in general, we're just playing around with the notion of what if you didn't have to worry about the topological linkedness of the input data, and you could just pull things apart.
But in this example, there's no like physics, right? It's just kind of like a.
Well, there's physics in the sense that you build the physics that you want, and that's the notion of control. The physics that we want here is we want a system that bifurcates on this disk, right? And so what we were going to do is we're going to learn a family of dynamical systems, which are the physics of this universe, right? So that we can control the initial conditions the way we want. So it's a kind of self-physics. But we're not examining a system in the world yet.
Right. I'm just asking you, this is kind of like you're trying to solve a standard discrimination task.
Exactly.
Where you're taking an input and giving it the label, and the way you're solving it is not like using a neural network, but by mapping these points to a differential equation.
Yes.
The overall goal is the same as kind of like traditional supervised learning.
Yes, in this case, absolutely. Although the I'm sorry, I don't speak.
12.
I will say, however, that these differential equations end up being neural networks. They're neural ODEs, except they're a neural ODE per point, right? So there's neural networks hiding in there, I assure you. So the math is a little bit, or the diagram of the flow of computation is a little hairy, but I think we've more or less gone over it. The basic principle of this application, or we want to learn one flow per initial condition. That's the idea. And the idea is that the parameters of a particular dynamical system are going to be output by some controller, some hypernetwork controller. And it's going to take an initial condition and it's going to map it to the initial weights of a controller function. And that controller is going to say, all right, I'm going to give my parameters to the flow that's going to actually act on the data. And if you like, you can close the loop so that the parameters will also change in time. So you can think of this as a kind of control system where G is a controller that gives the weights or the control variables to F, and F is the thing that actually acts on the data. And in general, what we would like is to have something like bifurcations on the space of initial conditions that disentangle the data. I put bifurcation in scare quotes here because it's not necessarily the topological sense. And if you allow the weights and the data to change together, you get this augmented system, which can be solved, and the parameters of this kind of hypernetwork, which learns the map from initial condition to dedicated system, can be learned either by backprop or by what's called the adjoint sensitivity method, if people have taken control before or in an engineering class. But that's a detail we don't need to go into. However, so there's some math if you would like to know about it. But the point is you can do backprop, and in practice what we do is we just use autograd like everyone does. And so the nice thing is, as you said, you can just carry out to these normal machine learning benchmarks. And what we did was we specifically compared our ENCODE system, which can kind of have this kind of anti-topological way of doing things, to competing continuous time nets, specifically on certain natural image tasks. So we did classification for MNIST and CFAR, and compared to...
what exactly is the loss function?
The loss function...
What you train with? How do you train?
So what we do is we have, for example, classification loss. and we can measure this classification loss in time. So for example, we have some softmax layer that's saying what's the probability of being this class, and we can integrate that loss in time, right? And what we want to do is we ultimately want to determine, we want to calculate the sensitivity of this loss to the parameters of the function taking an initial condition to its dedicated system here, which I've written here as gamma. And so more or less what we do is we integrate this thing, we get a scalar, and you can either just do backprop through time, which is laborious, or you can use the so-called adjoint method. The adjoint method is...
The scalar, what exactly does it measure? The Z of t is the output of the network at time t?
Yes, it's the output of the...
Dynamical system.
Exactly. And in general, it's the kind of augmented system where we have... this is just a very general way of writing it, where perhaps we want a loss on both the states and the weights as they evolve. Maybe we want a sparsity constraint, for example.
Okay, and then...
And so we just integrate it in time.
So ideally, if you could map directly to... I mean, where does the disentanglement come in? That's what I'm confused about.
I think that the disentanglement... I'm not a disentanglement guy, but... and I know they're here. So the disentanglement comes, I think, from the fact that you have one system per initial condition. And so what's being learned is how to take an initial condition to a family of trajectories that it's going to say, okay, initial condition, you go over here, and ignore what your neighbors do. You can cross, you can pull apart, you don't have to respect the homeomorphic quality that usually comes from these continuous deformations, which, by the way, are also present in regular discrete time neural networks, except there you can enlarge the dimensionality of the space. It's just usually how you get around it. So the fact that you have one of these per one of these is the disentangling aspect, as to my understanding.
So you get that, does it have a nice, for example, in the example with the sphere and the chunk in the middle, so like the simplest way would be, as you said, to push the center out. But
well, here we don't lift to another dimension. We're just pushing things around.
But how does it push it? Like, does it just because you could just shoot it to hell all the points?
Yeah. Well, that has to do with certain hyperparameters, right? How long you run the system, how fine you discretize time, things like that. But in general, if you use sensible hyperparameters, you run it for a little bit, you usually just get some type of minimal.
Because here it's nice, all the green points, they go to one spot, and all the yellow go to this line.
Yeah.
But I don't know, could have been less nice,
It could have been less nice, but you just at least want it to be linearly separable, right? And presumably, if you run this for longer, it's going to go for farther away, and maybe you'll run into some problems for that. And in general, understanding the way these flows work is not a simple business. I won't go into it now, but there's actually a way to incorporate this into a generative model, where now what you want to do is you want to map an image to a dedicated dynamical system that lives in a latent space, right? And then you run the dynamics up there in latent land, and then you decode from the final state. And the nice thing there is, instead of just doing interpolation like people usually do in VAE or something like that, you can measure the initial condition's evolution into its final decoded state here. So in general, I cut this off. This is not the initial condition. This is halfway through. You can see that you more or less start out with the same face, and as it evolves, this is the map. This is the decoded image. You can see that you can more or less look at the orbit as it manifests in the visible space, and we get favorable performances measured by this Ricci inception distance, which I don't remember, so don't ask me any questions about it. But again, general purpose control mechanism. I can go into this a little bit, but for the purposes of time, I'll simply say that we had suspicions that the chief advantage of this would be in the case of tasks where you needed flexible or dynamic recall. You give a system some data, you ask it to remember it in real time, and then do something with it. That's usually where control in engineering is important. And so I can go into the details if you'd like later, but what we did was we gave our model a little psychophysics task where we asked it to remember these long patterns of 100 or 1,000 bits. Here they're written only as 5. And then after a delay period, you give it a degraded version of one of them, and you say, okay, fill it in. So it's got to store something in its little dynamical synapses there and then recall that information for the purposes of reconstruction. I can go into the detail, but suffice it to say, at least for this simple experiment, we verified our intuition because compared to LSTMs, other recurrent neural networks, and other continuous time neural networks, the kind of closed loop feedback control of this mechanism worked very well, such that we got this bad figure so that the loss doesn't make any sense because it went to 0 immediately. But it's one of those things. I'll touch briefly on a return a little bit to physics and biology, whereby we used ENCODE in a recent manuscript to control dynamics, not just with a kind of random form where we just say, you learn any dynamics you want just as long as it works. Instead, we picked a classical model, which is used in computational biology, population genetics, physics in general, nonlinear systems in general, called the Kuramoto model, which, for example, is used to model the synchronization of fireflies. And if I hadn't done this in Beamer, I would show you a video of these fireflies synchronizing. It's truly amazing. So it's a nonlinear system that says when oscillators that are coupled to one another begin to flash or spin in synchrony. And so this is used all over engineering and biology. And what we would like to do is we would like to use this kind of control mechanism to take this equation, which has this complicated form here, and we want to force it to do what we want. So this is now a little bit more model-based and a little less model-free and more akin to what we started out by discussing, which is you have a system in the world, a real thing, and you want to understand how it works. And this required us to understand how to apply this, control technique to a system where only some of the parameters are varied and the rest of the system is fixed. And I won't go into the details, but the basic idea is that if you sample these random parameters, which show how the system tends to disorder, tends to desynchrony, how do you couple them together with these couplings Kij such that you can resist that desynchrony and you can keep everybody together? It's a kind of classical model of consensus. And suffice it to say, you can do all these fun things. So in the case of what's called global synchrony, if you have a system which is usually tending to disorder, you can use ENCODE to learn a map from those disordered parameters to those specific couplings which will counteract that disorder. So for example, in figure A here, this red trajectory in time is the phase, or the circular oscillator variables in time for the optimized system, and the blue is for the uncontrolled system. It's a little bit of a bad term I've used here because I'm using control in the sense of the experimental control. So this is the unoptimized version. So this laser-like red beam here is the controlled system saying we're synchronized, and blue says, sorry, we're spinning off to infinity. So you can learn how to create global synchrony. This is not just an exercise. This is useful, for example, in controlling power grids. If you have power grids, which are basically AC oscillators, if they're not synchronized, you can get blackouts. So figuring out how to synchronize these things when they have these inherently quenched random parameters is very important. You can also play around and make nice pictures and say, okay, maybe we don't want everybody to be synchronized, but maybe we want to have them synchronized in these clusters or something like that. And so now each one of these points is being used as input to the system, and we're learning the couplings that say, okay, let's couple these guys together, and let's make sure that they're all spread out from one another, just as a kind of mathematical exercise. And of course, you can make pretty pictures too. You can generalize from this to images. So now we have this color here is the U corresponding to the phase along the unit circle of these oscillators, which are now the pixels of a beautiful image of flowers. You can And so, suffice it to say, we get some good performance compared to control models. So this is a way of thinking about applying it to a real system in the world. So I'm going to conclude by talking finally a little bit about biology, and especially about some ongoing work in the Nitzing group with my colleagues, Zoe and Noah, who are here, specifically about the transition from control applications to prediction. We want to understand how parameter space works. We want to understand its structure. Where do catastrophes happen? Where do things go right? Where do things go wrong? You give me a system. I can put it in my machine learning model and say what it does, how many different things it can do. But before I go there, any questions? I hesitate to even know how long I've been going. Don't tell me. Okay, I'll continue. So one thing one has to learn when learning about biology, as I had to, is that you have to ignore a lot of stuff, right? And you don't care about certain details in dynamics. You care about largely the big picture. That's what diagnosis is about, after all. So you only care about the general shape of the dynamics. And you want to forget about other aspects of dynamics which you don't care about. So these are kind of dynamical invariances. So we don't necessarily care what particular arrangement the cells assume during growth in a cell-cell network, unless you're playing around with NovaSpark. You really care just about a distinction between two classes: healthy growth and catastrophic excitation in the form of malignant tumors or something like that. So we want to learn something like dynamical invariances. And so what we're going to do is we're going to play around with our old friend topological conjugacy. So we will remember this equation from before. So this is a way of saying that two flows are the same. This is a way of saying if you have one flow parameterized by lambda 1, one flow parameterized by lambda 2, if you can warp in a continuous way the orbits from one into the other, they're the same. So mathematically we say that the flows f lambda 1 and f lambda 2 are topologically conjugate if you have a homeomorphism that obeys this conjugacy relation for all t. So what we're going to do, and this is really ongoing work, so we don't have, so I'll benefit from your input to this. What we're starting to do is we're playing around with this trick which we call homeomorphic distance. It's a kind of, if you're a mathematician, you'll bristle at the conjunction of a topological and a geometrical term, but I'm sorry. So what we'd like to do is for every pair of parameters in a family of systems, we're going to find a dedicated homeomorphism. Again, this is this kind of dedicated idea, which is why the hypernetwork is lurking in the background always. And we wanted to minimize this kind of quasi-distance function, right? What do we do in machine learning? We take an inequality and we turn it into an LP loss function or something like that. And the idea is that we want to be small in the case that the systems f lambda 1 and f lambda 2 truly are topologically conjugate, and we want to be large otherwise. That's the signal we want to extract from this thing. And we're calling it homeomorphic distance. And the way we're starting to play around with this is with the following neural architecture. We're going to sample pairs of systems, f lambda 1, f lambda 2, and those give us these kind of phased pictures that describe how flows move through the system in a volume in the phase space. And we're going to basically treat them like images. Everything is an array when you're a computer scientist. And you stack them together and you push them through a convnet. And this convnet is supposed to look at kind of large-scale geometric aspects of these flows, and in particular integrate information from between the two. So you can get some kind of comparative, you can get a comparison between them. And what comes out of this hyper CNN are parameters of another system. Because remember, what we want ultimately is we want some homeomorphism that's going to try to warp this system into this other one. And so we've got to ultimately get that out of this. And so we spit out these parameters, we instantiate an ordinary differential equation from them, and we construct from that a flow, which you'll recall from our lesson is a homeomorphism, right? And so the output of this is supposed to be something that's going to warp this into that. And what we're going to do is we want to adjust the parameters of this network mu such that the average homeomorphic distance as you integrate through time is small. So homeomorphic distance, or average here, is taken over initial conditions and also pairs of parameters. So this is a loss of a hypernetwork. I'm going at 1,000,000 miles a minute, so if you want to talk later about this, suffice it to say that it's a way of detecting whether or not these two things are topologically the same. And marvelously, in a few cases already, this is from last week, you can get it to work a little bit. So what we're looking at here are these distance matrices where the x-axis is where both axes rather index the parameters of a one-dimensional dynamical system. And what we're looking at here is the hot spot means that the system has the kind of topological conjugacy net has learned that they're different, and black means that they're the same. And so a block structure like this indicates that the system has learned correctly. Why? Because the system does undergo a bifurcation at this point right here. And so the hot spot here and the hot spot here and these kind of zero aspects on the off diagonal indicate that, yeah, for this oscillator, you've learned a way of extracting a topological structure. You can get the same thing more or less for a pitchfork bifurcation, but for the saddle node family, which I won't go into, it's much harder for technical numerical reasons, which we can discuss. So amazingly, you can now just sample random oscillator systems and then classify them using any distance-based clustering. Yes?
Yeah, sorry to stop you.
No.
So this is all dependent on the resolution of your Facebook.
Absolutely.
Right, so it's very, very dependent on it. That's what I'm trying to mean. So how
Indeed.
do you take this into account?
Well, for the moment, it's just a little bit like alchemy, right? You pick a resolution in the phase space, you pick how long it's going to run, you pick the resolution of the temporal integration, and it either works or it doesn't. But like many things, you find a kind of Goldilocks zone. It just seems to work, and that's what we're looking for.
In real life, you won't. I guess you won't know what the resolution. You won't know what the real dynamics you're looking for. Like here.
Yeah.
I guess you know what the dynamics are supposed to be.
Yes, and so we wouldn't know. We know that this is right because we know what the bifurcations are, right? But for a real system, ideally, what we would like is just some distance matrix that just pops out of it, and then we can make a judgment using that. And that will require some matching of hyperparameters and things like that. Where you can actually observe the way these flows work, but we don't need to go into that, although it's a very pretty picture I'm proud of. And this is mostly for Zoe and Noah. Last night, I played around with measuring the homeomorphic distance between systems that actually have different equations. So these are two different oscillators, a Fitzhugh-Nagumo oscillator and a simpler one. And you can still pull out that structure a little bit. And this is what we're starting to get at. We want to get at a very general notion of measuring dynamics in general, oscillator-ness, fixed point-ness, etc. And what I'll close with is perhaps the most directly biological application of what we're working on, which is a way of replacing the loss function here with a simple reconstruction loss. So you want to reconstruct the flows. And if you try to reconstruct the flows, perhaps by also enforcing a kind of minimality constraint on the circuit or the dynamics that's reconstructed, you can learn these nice latent manifolds of dynamical behavior. And they end up looking something like this. So this is a one-dimensional manifold that's learned from a family of dynamical systems. Every point here is an equation. You extract the correct dimension. This is a one-dimensional manifold for a one-dimensional system embedded in a 16-dimensional ambient space. You can do the same thing for a much more complicated model like a Hodgkin-Huxley system, and you get these nice structures, which we're looking to explore. But this is more than a party trick because, as I said, if you enforce sparsity on the output, you can start to reconstruct circuits and dynamical models that carry out the same dynamical function and yet are sparser. And what we're trying to get at here is the extraction of minimal design principles or circuit principles in the case of certain cell-cell or gene regulatory systems that control biological function. This is one from a celebrated paper from Oriolone's group, whereby a population of cells interacts with a population of ligands. And what we did was we can use this system to pull out minimal models which give rise to target dynamics. I can go into it at the cocktail hour. So the big ideas are, I'm interested in families and not just systems. We want to talk about control and prediction, and we want to keep an eye towards these key systems in computational biology, namely gene regulatory networks and cell-cell interactions, which we're kind of hoping to get to soon, although I've presented mostly abstract work to you today. And with that, I want to thank my excellent and brilliant colleagues and advisors, Mornitsen, Zoe Piran, and Noah Moriel, along with my colleague from Brown University, Mathieu Charvidal, and some of these other people. And with that, I'll take your questions and tomatoes and everything. Thank you.
Are there any more questions?
Just a small question, but the distance you showed with the homomorphism, you get a H12 homomorphism.
This one?
Yeah. So, do you try to, isn't there supposed to be also like an argmean H12 such that the distance is minimal?
Well, the idea is that you just want to try to minimize, you want, for every pair, you want to try to find an H2 such that this is minimal. And what you're hoping is that in some cases you're going to be able to minimize it all the way to 0. And in other cases you're just going to run up to the fact that such a thing does not exist, and so this will be large. So you're trying to minimize it everywhere, right?
So you're checking different homomorphisms and saying how well they do.
Exactly, and you're not just checking them, you're outputting them from this function in a kind of fully differentiable way.
Yeah. Is there like, this seems a little bit kind of indirect, where you're kind of putting, encoding the dynamical system into an image and then inputting it to a network. Can you just like minimize or find this H with more kind of just solving a bunch of equations, or?
Well, I mean, in general, detecting when two things are topologically conjugate is hard. So you're talking about analytically, or you're just talking about like just work with time series?
I mean, I guess this is like a known problem, right?
Yeah.
Just wondering, like, what's a more kind of
like a classical way of doing this? So usually, what you do is you just you try to find H explicitly, and there is work again from Steve Brunton's group doing this for the single system case. You just optimize a single H for a single system and you stop. The only thing that's really new here is you do it here. You're just doing it in the enlarged scope on the whole family, and that's the only thing that's new. Analytically, classically, what you do is you just you take a guess, you make an ansatz, and you put it on the table. This is a little indirect, and naturally we're trying to find the thing that's going to be most amenable to real data, and so this is an evolving situation. Yes. Any last questions? Yes.
Can you think about finding these ages in instance of the optimal transport problem? Like finding the...
Yeah, okay. So you have like a distribution over functions or something like that?
Yeah. And trying to find the transport and minimize the distance between...
Yeah, that's a very good point. And it would be very interesting, since there are great experts in our group in optimal transport, to unite those two ways of thinking. I haven't, and in fact, I think I Googled this at one point, optimal transport conjugacy class data or something like that, and nothing came up. But maybe it could be you who does it.
But the thing is, it will just map you. It's harder to find like classes. You could use a very center approach where you come up. Notion about optimal transport and just map it to prediction. You'll just get a map, and it will always find a map. It won't say these can.
And remember that the mapping has to obey actually very stringent conditions, right? You're not just pushing around dirt like your Gaspard Monge, right? you're trying to find this very specific function in the form of a homeomorphism, right? It's got to be invertible. Think about that. I guess I don't know if the transport map has to be invertible. Or probably not.
It will map. But the thing is that the transport map will always map. So it will find mapping, and you go back and forth, but it won't tell whether it won't be a homomorphism.
Yeah. But that's it'd be interesting if you put that as a constraint in an optimal transport problem. Well, I don't know if such a thing is possible though. All right. All right. Excellent. Thank you again.
So thank you.
Yeah.